Wen, sorry. And title is a classification of some 3+1 dimensional topological orders. So please.
Yeah, first I'd like to thank the organizer for organizing such a exciting workshop. The mixture of charismatic people and energy people are really exciting because bring very different, very fresh point of view to look at the similar problem. And today, what I'm going to talk about have a slightly different emphasis because I will not discuss the physics near critical point, which is described by field theory. So I try to describe physics very, very far away from critical point. So in some sense, the physics I'm going to discuss is not field theory. But however, it's still called fully extended unitary topological quantum field theory. So somehow this field theory is a so powerful name, so people want to use that all the time. And mathematically, in condensed matter, we call this a topological order. In mathematics, this may correspond to so-called braided fusion 2 category, or this unitary topological quantum field theory. So this may be related. Okay, so today I'm going to emphasize concentrating on this 3-dimensional or 3+1 dimensional system. And a topological order in 1 dimension or in 1+1 dimension has been known, means there's no topological order in 1+1 dimension. And in 2+1 dimension, we also kind of know systematically. It's related to the tensor category theory or modular tensor category theory. And for a while, maybe for a long time, we kind of puzzled, how to have a systematic theory for 3-dimensional topological order, or for 4-dimensional TQFT. So basically, whether there's a systematic understanding of a 4-dimensional TQFT or 3+1 dimensional topological order. And so today I'm going to discuss some recent work trying to make some progress in this direction. And the result we obtain is very surprising. It's too simple because 4-dimensional manifold is supposed to be very, very complicated and seems it's a very hard problem. But the result we get seems even simpler than 2+1 dimensional topological order. So maybe we missed something. And so we'll see. And so to discuss a 3-dimensional topological order or 3+1 dimensional topological order, we should notice that there's a point-like excitation and there's a string-like excitation. Just like a Z2-gate theory, we have a Z2 charge, which is a point-like excitation, and this Z2 flux is a string-like excitation. So basically, we have to deal with both point-like and string-like excitation. Okay, that's the first point. The second point is that for the point-like excitation, they cannot have a non-trivial mutual statistics. When you try to braid one point around another, this braiding can always unwind, so always a trivial braiding. So therefore, because the trivial braiding, so this point-like excitation can only be boson or fermions. And then there's a very formal mathematical name for that. It's called the symmetric fusion category. So all those point-like excitation are described by so-called symmetric fusion category. And so when you ask what kind of point-like excitation you can have in 3 dimensions, you can ask basically what kind of a symmetric fusion category can you have. And fortunately, mathematicians gave us a full classification of a symmetric fusion category. Basically, it's a representation of finite group. Every symmetric fusion category is a representation of finite group. So that's very simple. And but certainly there's a little bit a twist. That is, sometimes we have fermions, and so when you have fermions, this finite group is more special. The finite group is a Z2 times another finite group, but not really a direct product. this notation means Z2F extension of a GB. So it's not a semi-direct product. I don't have other symbols. I invent this symbol. So this really means Z2F center expansion over GB. So that this symbol. So this it have this kind of structure, and then the representation where Z2F is represent non-trivially correspond to fermion, and the representation of GB only where Z2F is trivial, those are bosons. So therefore, still the particle is representation of a boson fermion, but depend on whether Z2F is trivial or non-trivially represented. Okay. So then we immediately get a conclusion here. Every three-dimensional topological order have a group. Somehow there's a hidden group inside every three-dimensional topological order. So that sounds like a gate theory. So actually at the end, it is this case. That's the three-dimensional topological is very much like a gate theory, but with some twist. And then we have the strings, okay, the loops. And then here, when you have loops, actually we must have loops. The reason is following. When you only have particles, the particle cannot satisfy this principal remote detectability. Actually, Michael talked about that yesterday, which is a very important assumption in a topological order. Basically, it says that every topological excitation can be detected by other topological excitation remotely. When you only have particles, because trivial mutual statistics, so the particle cannot detect other particles. So we need the loops to detect particles. And but maybe so therefore for every particle there is a loop which have a non-trivial mutual statistic with them. For every loop, there are either particle or other loops with non-trivial mutual statistics. So these non-trivial mutual statistics kind of tie everything together, and so that's almost the end of story. So this object which have a particle have loops with non-trivial mutual statistics, and this kind of mathematical structure also have a scary name. It's called a four category. I don't know what's the definition for the category, but it's something related. It's a non-degenerate really means that for every object or morphism in four categories can be detected by other things. So there's some non-degeneracy there. Okay. So here I just try to link to some kind of mathematical terminology in the four category. In the category theory, have a object and a morphism and etc. In physics, it's pretty simple. These four categories have only one trivial object and one trivial, one morphism, but they have other non-trivial two morphism, three morphism. So what is that? Actually, in physics, one object means unique ground states on sphere. So that's very simple. And there's only one trivial one morphism. So basically, there's no non-trivial morphism, means that there's no domain wall excitation. So the only excitation are string-like. There's no membrane-like excitation. And the reason also very simple. When you have a membrane-like excitation in 3 dimensions, there's nothing to remotely detect the membrane because you cannot braid around the membrane. So therefore, so membrane is not allowed. Although in principle it is allowed, but to have a realizable topological order, membrane is not allowed. So that's why in category we say we have a trivial one morphism. But this two morphism is just a mathematician's way to say, yeah, we have strings. And the three morphism means we have particles. So that's it. So basically, this four morphism basically say we have something with a particle and strings. But however, in this mathematical description or this braiding and fusion, this consistent structure can be put into place. Just another way to do that. Okay. And there's another way that we can drop this because these first two layers are trivial. So we can drop this first two layers and view two morphism and object, three morphism as a one morphism. Then this same thing can be called unitary Bragg diffusion 2 category or something along that direction. And so from this unitary Bragg diffusion 2 category, we should get the result that this the particle or this the particle are described by a group, a representative group, and the string are actually described by conjugate class of group. So again, there's group structure. However, this picture is very abstract since we just have a words for the category. There's no understandable data. There's no numbers. So we hope we have some data which, like a number, to describe a characterized topological order.
What kind of groups? Is it finite groups or?
Finite group. Actually, continuous group should be very natural. Why continuous group is not allowed? Because continuous group have an infinite number of representation. That means you will have a topological order which particle type are, there's an infinite type of a particle. And there are some problem with that. Let me see. The close analog I can have is like you have a U1 gauge theory in 3 dimensions. The charge have infinite type because the charge is integer, can any integer. But then when the charge is any integers, then you'll find you have a gapless gauge field. So actually the gauge field is gapless. So this situation is not gap, it's gapless. Or you may say, okay, let's do SU2. The charge, the representation SU2 is a positive integer. But again, the SU2 gauge field may be gapless. If it's not gapless, it may be confined, then become trivial. So somehow the infinite group is ruled out. Only finite group enter here.
Sorry, how do I start from infinite number of representations and go to the conclusion of gapless? So what's
it's kind of the flux. When you have infinite number, it's there's some intuition there, but I couldn't say very precise. It's a representation still discrete. Looks like to have a charge is okay, but your dual somehow have troubles. Then that became gapless. So the flux really when you have even number of representation, it is a flux which became gapless. Yeah.
And what if the word unitary stands for? You didn't assume unitarity.
Unitary. What unitary? You mean unitary?
Yeah.
Well, I don't know. Every physics theory is unitary. So basically, in category theory, there is a vector space. So this vector space is assumed to have a complex number based, and there is for every vector space there's inner products defined. So there's a dual and.
So this does not include interesting topological quantum field theories like those that Witten constructed, the twisted theories.
For non-unitary one, no.
Witten constructed an extremely rich topological field theories in 4 dimensions, which compute tunnels and Witten invariants.
Yeah. So I don't know about this, but from my understanding, that's for gapless theory, not for gaps theory. So whether this so that actually maybe we should discuss this because I know there's a higher dimension topological invariance, and my understanding that's a gapless supersymmetric theory with a twist boundary condition, and the zero mode looks like a topological theory, and the zero mode became non-unitary topological theory. Actually, so because it's a zero mode of a gapless theory, they are not unitary, and so actually that kind of topological theory is better to be a theory for critical point, not for gapped phase, and here is for gapped phase. But I don't fully understand that, so I just say my impression, and I need to understand more about this. Yeah. So actually now I try to do some more concrete because the first description is too abstract, and so let's do something more concrete. And so here we want to divide this 3D topology in 2 classes. And one simple class is where all the point-like excitation are bosons. So there's no Fermion. Every point-like excitation is a boson. So that's a simple case. Okay, in this case, we have something more concrete. First, in the more abstract language is that this kind of topological order are described by this pointed fusion 2 category with only trivial morphism. Okay, that sounds very abstract. Or by a pair, a group and a group focal cycle. And this maybe nowadays, this probably is more familiar. So at least a group co-cycle probably is a lower term in physics. And so it is a focal cycle because we do 3 plus 1 dimension. So this 4 means space-time dimension. Okay, so this pair classify every 3-dimensional topological order where the particle-like excitation are bosons. Okay, so how this was obtained? So actually, the argument is pretty simple, and the key point is that every 3-dimensional topological order have a unique canonical gapped boundary, which we only have a string excitation. Okay. So what that means is that we try to, because all the particles in this topological order is assumed to be boson, so we can condense all of them. So you're condensing all of the boson, then you get a new topological order where all the particles condense, so there's no particle. So this new topology can only have strings. Then you can argue that the topological order with only strings must be trivial, because the string braiding among themselves cannot support this remote detectability principle. So string cannot detect each other by themselves alone. So if a topology with string only has to be trivial, the string has to be trivial. Okay, and then that also means that you can condensing the particle to form a boundary to the trivial phase, because condensing every particle gives you a trivial phase. So you can condensing all the particles to get a boundary which connect to trivial phase. And this boundary will be the string-only boundary. Yeah, so this boundary will be we call all-string boundary or string-only boundary. So every 3-dimensional topological order have a string-only boundary. So this is basically that's a key observation. And from here, we can get everything.
Braiding actually it violates the remote detection principle, something like that, or this is non-trivial 3-loop braiding, right? So.
Yes. So let me see. Okay, let me put it this way. Yeah, 3-loop do not matter, but the point is following. Suppose you have a single loop. So if you have a string, that's my argument. My use of this is following. Let's say I have a single loop. Then I say, I need something to detect this single loop. If I only have a strings, then I have to use another string to braid around this single loop. And so the single loop has to be trivial, basically. So that is the argument.
Sorry, I thought 3-loop braiding.
Yeah.
We need 3 loops, right? So it means if I want to detect 1 loop, well, we need 2 other loops.
Yes, but here we're trying to show that the single loop has to be trivial. I cannot have a non-trivial single loop. And the 3-loop braiding is kind of, when you have a non-trivial single loop, then you can link a single loop to get a more complete configuration. And here I try to argue that the single loop has to be a trivial loop, because existing single loop, this single loop cannot be detected by other things. Yeah. I cannot say this. Certainly I use this remote detectability in certain ways, and so there's, and I understand. So maybe this conclusion is not quite correct. So even when single loop is trivial, but the linked loop can be non-trivial. Whether that could be a situation. Yeah, that I don't know. But here I try to say that every single loop has to be trivial loop, because we cannot detect single loop by braiding with other loops. So that is the argument I use. Then suddenly I use this to jump into, when you don't have any single loop, the topology must be trivial. That's a jump, And so I cannot say this is a rigorous proof, but this is the kind of argument we use. Okay, so so this became a key step. That is, by condensing all the particle, one can obtain this the O-string boundary. And then on this O-string boundary, then we can using this shrinking operation. In the bulk, when you're shrinking a single loop, you may get some particle, either trivial particle or some other trivial particles when you shrink a single loops. But however, on the boundary, the same loop, same string on the boundary, because boundary, all the particles condensed become trivial. When you shrink loop on the boundary, you can only get a trivial particle. There's no other non-trivial particle. So therefore, so that really means that when the bulk string moves to the boundary, it is split into direct sum of several boundary string. Because this string, when you shrink, becomes several copies of identity trivial particles, means it can be viewed as accidental degeneracy of several boundary string. So actually, that really means that the shrinking of a boundary string can only give you identity. That's a shrinking operation. And that means that the boundary string have an internal degree freedom of 1. So there's no non-trivial internal degree freedom. Or more formally, we say it have a quantity dimension 1, because shrinking of a loop give you identity. And so that really means that the fusion of those boundary string has to be pointed, means that fusion string 1 and string 2 can only give us a single third string, not a sum, not a direct sum of several other strings. So therefore, this is mathematically called the pointed fusion rule, or in physics you can call this a fusion rule, just like a group multiplication. So naturally, that's how we get this group. Okay. And so therefore, the all string boundary, the string fusion is a group-like. And then actually the hard part in this argument is that this string fusion group and this the bulk group from the particle excitation, they are actually the same group. Now this is a kind of non-trivial. But again, there's Tanaka duality in mathematics. Actually, the proof is very much like a proof of Tanaka duality. So this the string fusion on the boundary and the representation of a bulk particle, they're actually coming from the same group. Okay, so because all the particles condensed, the boundary only have a string, no particle. So then in mathematics, it shows us we only have an object, no morphism, because object is a string, and one morphism is like a particle, like a domain wall on the string. So that's a particle. But we don't have a particle. So therefore, we only have a category theory of strings. And this is formally called a two category, or a fusion two category. Because the fusion of a string is a group-like, so that's called a pointed fusion two category with no morphism. So that describes this three-dimensional topological order. So that's how we get results. And then there's again, I think there's a mathematical result says it's a pointed fusion two category can be also labeled by the group and the focal cycle. So there's a mathematical result. And so this is related to the so-called this. So let's see. So this doesn't move. Frozen. Oh. Oh. Okay.
So are you just talking about TwoGate theory? 3+1 dimensions?
Almost. And I'll come back to that very quickly. And so here we just describe a boundary. And actually there is a relation between boundary topological order, which is anomalous, and the bulk topological order. So actually, every boundary topology order corresponds to a unique bulk topology order. But there could be several different boundary topology order, anomalous one, correspond to the same bulk topology. But however, but once you determine the boundary, the bulk is uniquely determined. And so by describing, so this point diffusion two category are describing boundary strings. But once the boundary is fixed, the bulk is uniquely fixed. So that's why we use a boundary theory to classify bulk theory. And so now this is gauge theory. So actually, this more explicit classification gives us a very explicit realization. So not only we have this classification of this all boson topology order, but we know how to realize each of them. So the idea is that we can start with a bosonic theory, but this boson field live on the triangulation. And in particular here, we say the boson field live on the link of the triangulation. You know, kind of like a Torah code model. They live on the link of triangulation. Okay, then how to use this kind of bosonic theory to realize the topology order described by this category theory, or two category theory. And then the idea is that this bosonic field on the link have a value in a simple object. You know, in the fusion two category, there's an object. And a simple object give you this value of a bosonic field. So that's another way to say this bosonic field live in a finite group, because the object labeled by group elements. So actually, so we have this group element live on a link. That looks like a gauge theory. Yeah. And there is no field on the triangles. So we only have a field live on the link, but nothing on the triangle. This corresponds to there's no non-trivial one morphism. Yeah, there's I missed a no. There's no non-trivial morphism. Okay, so there's no field on the triangle. If there's non-trivial morphism, we also have a field on the triangle, and we'll see later. And so then there's a flat condition. This is the fusion rule. Basically, the fusion rule gave us a flat condition of this gauge field, or gauge theory. And so if this Lagrangian is taken to be 0, then we get the gauge theory. However, there's a more general gauge theory. If we can choose this Lagrangian to be a focal cycle, we get this well-known Digraph-Witten theory. So basically, the conclusion is that for three-dimensional topology order, if all the particles are bosons, then they are classified Digraph-Witten theory. So it's a pretty simple conclusion. It's also surprising. Maybe we missed something, maybe not. But at least there's an argument, try to argue, yeah, this all boson topology order just Digraph-Witten theory. So twist the gauge theory.
Sorry, why can't you add discrete two-form fields to the Lagrangian?
Because here we don't have a one morphism. So by using this, we'll realize all boson. We realize all the boundary we constructed. So realize all the boson topology. We don't need to do that. Your question, I understand. The question is a very, very valid question. So you have more general topological theory. And here I try to say that adding these two fields don't give you new theory. So that is a big conjecture, because the way to construct topology theory is much richer than described in here. But I say there's a duality. They are all equivalent. Most of them are equivalent. And so if those topologies don't have bosons, even with two-form field, the equivalent to the Digraph-Witten theory. Yeah. So that's I don't know. Yeah, there's a lot of duality here. Yeah. Everything with a two-form field.
But is that something that one can see explicitly, that if you add some two-form fields, you can convert it into another group?
I hope so, yeah. And that's way to, actually that's one way to check whether we miss something here or not. And so the idea is that when you're condensing all the particles, you will get all string boundary. And so that's a clue. Do you get a different all string boundary, or maybe we're missing something in the argument? Yeah. So, but indeed the conclusion of this is that the topology theory with two-form field are equivalent to one gauge theory, the Digraph-Witten gauge theory, if you don't have fermions. Okay, so now let's try to add fermions. So when you have fermions, what happens? And So as I mentioned that when you have fermions, the particle is still described by representation of a group. But this group is a Z2 extension of another finite group, have this kind of structure. And the Z2 extension is non-trivial extension, so labeled by these two co-cycles. Okay.
So these fermions are gating random fermion or not?
No, they are bosonic. So topology order is a boson topology. They are emergent fermion. So I do not do fermionic topology. Always is bosonic one. Yeah. So this we call the emergent fermion topology order. So EF topology order. And this EF topology can divide into two classes, EF1 and EF2. So we'll describe EF1 first, but we pretend we describe everything. And so this one is a pretty, result is also pretty simple. It's a unitary pointed fusion two category. So it seems the same, but only one difference that the object is still described by this fusion. But the fusion are really objects are labeled, or this boundary string are labeled by GB only, not by this GF, by GB only. But in addition to the boundary string, we also have a fermion. So there's a point-like particle live on the boundary, which is a fermionic point-like particle. So compared to this all boson topology order, we have a point fusion two category, but no non-trivial morphism. But for EF1 topology order, the boundary is again a point fusion two category, but with only one fermion, which is a fermionic one morphism. So this just adding this one fermionic one morphism is only distinction. And how do you do the proof? Let's do that very quickly. And idea is again same. We want to condense the particle to get the boundary. But now some particles are fermions, so we cannot condense them. We can only condense those bosons. So we try to condense all the bosons to get the boundary. So when you condense all the bosons, you get another topology order. In this topology order, the only particle is a fermion, just a single fermion. And then you have this Z2, it's like a Z2 gauge field. You have a Z2 charge and Z2 flux. So you have a fermion particle, you have a loops excitation. But however, this point fermion, this Z2 charge is fermion. So you can twist the Z2 gauge theory. It's a fermionic Z2 gauge theory. Okay. And then in this boundary, in this domain wall, we have a string labeled by GF. So this domain wall also only have strings and also fermion particle, but the string on the domain wall is labeled by GF. But however, for this Z2 fermionic gauge theory, we can get another domain wall by condensing the Z2 strings. Because the particle is a fermion, we cannot condensing that. We can condensing Z2 strings to get the boundary. So Z2 string became trivial. When these two boundary, when the domain wall and the boundary are close together, then the string on the domain wall have been quotient out by this condensing the Z2 part of a string. So that's why in the combined boundary, the string are GB. It's a Z2F quotient out Z2F. So that's explain why the string is a GB, and a certain particle is still there. So therefore, we have a E2 this string with the particles, and that's it. So the string with only one fermionic particle is not too complicated, and so there's a mathematical theory to describe them, and actually there's also a explicit realization of this E1F topology order. And the idea, again, is very similar, is that we have the boundary string became a label on the link. So this link variable became GB. So on the link, we have a GB. But now the boundary string can have a particle live on that. So that's so-called one morphism. And one morphism says that when you try to realize this kind of boundary theory, we should have a field on the triangle as well. So that's B1, B0, 1, 2 is a field live on the triangle. But because this boundary particle is a fermion, either trivial or one fermion, so just it's a Z2 variable. Two fermion fusion give you trivial. So therefore, this field live on the triangle is a Z2 variable, just a 0 and 1. Okay, so this is this Z2 variable 0 and 1. So this gave rise to this two-form gauge theory. So it's kind of like an ordinary gauge theory. We have a group live on the link, but now we also have some Z2 field live on a triangle, and that is called a two-gauge theory. This kind of beast called a two-gauge theory, and there's two group, and where the pi 1 of two group is GB, pi 2 is Z2. So again, we make a very strong claim here. That is every two-gauge theory depend on arbitrary two group belong to either Dagrange-Witten theory or this kind of a two-gauge theory. So there's again a lot of duality here. Yeah.
So it's basically the same on the previous model where you gauge the Z2 center symmetry.
I don't know what is, because here what I try to say is that we have a three-dimensional bosonic system which have a gap phase, and there's emerging fermion. And so you can say I don't start with a group, I do not start with gauging. But however, this the fusion of a particle is either like a boson or fermion, and they behave like representation of some group. Indeed, it's like a gauge everything. We're gauging the fermionic parity symmetry and gauging everything, and but if you're only gauging this fermion parity, you don't get that, because if you do the Dagrange-Witten gauge theory, all the particle, all the charge are bosons, and you have to do something to make some charge a fermion, and so this actual two-form gauge field on the triangles just do that trick. When you do that, you can convert some particle to fermions. And the claim is that that's everything. So you can write down the more general two-form gauge theory. And the claim of this result is that other two-form gauge theory are equivalent to either Dagrange-Witten gauge theory or this particular subset of a two-gauge theory with a very special two-gauge group. Yeah. So basically the subset of two-gauge theory classified the so-called EF1 topology order. Okay, and that looks like the whole story. That's all. That's very nice. The Dagrange-Witten gauge theory describe all boson topology order, and two-form gauge theory describe this emerging fermion topology order, and that's all the three-dimensional topology order. Almost, that's 2/3. Actually, we're missing 1/3. And so I try to explain the missing part. Yeah.
If N3 is a co-cycle, why is it a co-boundary of B? In the previous slide. If N3 is a co-cycle, why is it a co-boundary of B?
So there's some constraint.
You're talking about the equation GB is.
No, the N3 is.
G to pull it back.
Yeah, it's there's some pulling back. Yeah, there's I'm sorry. Yeah, this is more complicated. So basically, yeah, maybe let me skip that. There's this room is a trivialization. There's some trivialization going on here. Yeah. But it's part of the story of defining two-gauge theory. I did not go into that. So when you try to define two-gauge theory, those kind of structure all pop up. It's part of the definition of two-gauge theory. Yeah. So what is missing? So we missed something here, actually. The story I discussed is not complete. So what is missing? And then here I want to go into something more detailed. So here when I say string, I really mean a type of a string. Means some excitation, some equivalent class of excitation. It's like two quarter particle. If they can deform each other, they belong to the same type. When two strings which can deform each other, they belong to the same type. But there's a shortage in definition of type of a string. Here, I'm using a very dramatic definition. We use a non-local unitary transformation to define type of string. And this is important. Okay. but it's overkill. It's too much. So there's some subtlety in my story. And so far when I discuss string type and the group fusion rule, I really using this non-local unitary transformation. But to use category theory, I think the right thing to do is using local unitary transformation to define type of string. On a particle, it doesn't matter. Particle is a point. Non-local, local is the same thing. When you have a string, there's distinction. The membrane, even more distinction. So whether using local unitary or using non-local unitary to define type of string, we struggle on this issue for maybe 5 years, and we still don't have a very clear answer what should be done. The reason is that we want to use non-local because we do not want to, when you have particles, those particles can condense into some topological phase, and we do not want to regard those topological phases from particle condensation as a non-trivial string or membrane excitation. So this using non-local unitary can remove that, so it's very nice. But non-local unitary seems is overkill. So after some struggling, so we back to L type. L type is using local unitary to define string type. And once you're using local unitary transformation to define string type, so I think that this should be a right way to define string type for the boundary string. And this allows something new. That is, we could have a string decorated with a one-dimensional pure topological superconductor, which is proposed by Gitev. Yeah, okay. So this because the boundary have a fermions. The boundary fermion can form this P-wave topological superconductor, and that's also a string. And this string can combine with my original boundary string to make a more general, more boundary string. So therefore, the total boundary string type should be the ZGB, that's the older one, times Z2, which is this 1D superconductor, the P-wave superconductor string. Okay. But then there's some subtlety. If it's only just this kind of direct product, then we can really drop it. We don't need that, and so my order result will be correct. So that will be the EF1. But however, this 1D topological superconductor is called an invertible topological phase. So we only know if two strings are different by this topological superconductor or not. We are not sure which one have it, which one don't have it. And sometimes there's obstruction to say which string carry this P-wave superconductor, which string don't carry. There's no way to consistently to say to have this division. So this class string have it, the other string don't have a P-wave superconductor. So that really means that in this case, the string are labeled by this non-trivial product between non-trivial Z2 extension of GB. So this gives us a new type of a Fermionic topology order. So the string basically, I think this may be a general phenomenon. When you can decorate a string by invertible topology order. But however, this decoration can be twisted. You don't know which one have it, which one don't have it. This is as a tosser. This kind of tosser-like decoration give you this twisted tensor product, and that gives you a new kind of boundary theory. And this new kind of a boundary theory, let me just describe this part. This new kind of boundary theory is that it have a string labeled by this Z2 times GB, and also have a fermion before. But it have one more thing. The two string differ by this Z2M. They have a domain wall. This domain wall happen to be the boundary of a P-wave superconductor, which is a Marana-zero mode. So there is one morphism behave like a Marana-zero mode, and so that's all. And so this is three. So EF have two parts, EF1, EF2. So after you consider this decoration of Marana string in this twisted fashion, we believe we have a full story. So that's really our proposal or conjecture the classification of three-dimensional topological order. Okay, that's it.
So I'm just wasn't clear to me. So in the bosonic case, you had an argument for why you get everything based on condensing, based on some axiom about boundaries defining a bulk uniquely.
Yeah, that's right.
Is there a similar kind of heuristic argument for why this gives everything, or in the case where you have fermions, or?
Yeah, basically, to claim classification certainly is very dangerous, but we try. And so we try to construct the most general boundary. Basically, that's what we try to do. And it seems to me that we have a fermion. So we construct. We already argue that the boundary can only have a GB string and a fermion. But plus this period shipment decoration, we only have this. We add one more twist, and we couldn't think about any other twist. You can think of, you can decorate other particle, but other decoration cannot have this twist product. You know, you only the topological 1D topological face can have this torsor-like twist product. So basically by arguing the boundary at the most have this structure. So that's our argument. The boundary at the most have this structure, and then from there, then bulk at the most have this structure. We may miss something, but one can try to see what we are missed. Maybe boundary can have you can add some more structure in boundary, but so far we couldn't see any other structure we can add. So yeah, that's basically the taste of argument. Yeah.
Okay, let's thank the speaker.